Welcome to Introductory Chemistry with Dr. H. This is a content video about intermolecular forces. This is the first content video on that subject. Today what we're going to talk about is classifying intermolecular forces and their characteristics. Before we do that, we're going to do a little bit of context to understand why we need to think about intermolecular forces. Then we'll go through the different types of intermolecular forces and how to classify them and talk about their characteristics. Then we're going to discuss a process of determining what intermolecular forces are present in a solution or in a substance. And then we'll talk about representing intermolecular forces with a drawing, which is a really important skill. So first, intermolecular forces, what are they? We have this picture of how atoms and molecules in a gas behave in that they're zipping around in space and they rarely encounter one another. So, they're moving around in all sorts of different directions. They rarely collide. When they're far apart like that, they don't have very many attractive forces between them. That's the reason why they're gases. The atoms and molecules move all over the place. They fill the shape of any container that they're in. Rarely do they encounter one another. However, when you increase the pressure or you lower the temperature, if you increase the pressure, you push those atoms or molecules closer together. If you lower the temperature, they have less and less kinetic energy. And then occasionally, when they come in proximity with each other, they do experience an attractive interaction, and that attractive interaction is an intermolecular force. And if the intermolecular forces are great enough, those gas molecules will condense into a liquid, meaning the atoms or molecules are close enough together that they're constantly having attractive forces between their neighbors. And so, a liquid has dynamic molecules or atoms, meaning the atoms or molecules are moving around, but they're close enough that we see between any molecules or atoms that are close together, you see these attractive forces. Those are the intermolecular forces. And the strength of those intermolecular forces determines how easy it is, say, to punch one of those molecules back into the gas phase. Say, how hot you need to heat a liquid before it boils and it becomes a gas again, right? So if you have strong intermolecular forces, you're going to have a higher boiling point. So those intermolecular forces can be quantified with a number of physical properties. Now, if you continue to increase the pressure or cool the temperature of a liquid, we know that it will solidify, right? When it solidifies, the intermolecular forces are sort of even more important. In a solid, the atoms or molecules are held fixed in a lattice, and they're held fixed in a lattice in such a way to maximize the intermolecular forces between those atoms or molecules that make up that gas or that liquid. So intermolecular forces are even more important. In going between the phases of matter, for example, the energy that it takes to move between one phase and another is dependent on how strong those forces are. So that's just a sense of intermolecular forces and what they are in different phases of matter. So one sort of challenging part about understanding what's going on when we're talking about intermolecular forces is the distinction between intermolecular forces, forces between things, and intramolecular forces, forces within things. There are a number of things that are confusing about this terminology, so let's just straighten that out right away. I've drawn a picture here of two different water molecules, and water has a fairly high boiling point, a very high boiling point for a substance that has such a low molecular weight. And the reason why it has a relatively high boiling point is there are strong intermolecular forces. There's a positive dipole on hydrogen atoms and a negative partial charge on the oxygen atoms as a result of the dipole. And those positive and negative charges have a Coulombic attraction that hold those things together. In an optimal hydrogen bond, it takes about 40 kilojoules per mole to break one of those intermolecular forces. We call it a hydrogen bond. That's a fair bit of energy. So it requires energy to boil water, and that energy is going into breaking up all of those intermolecular forces that are holding those molecules of water in the liquid phase. So that's what we mean when we're talking about an intermolecular force, an between molecular force. There are two different sort of meanings of the word intra. If you want to think about an intramolecular force, one interpretation is the bond that holds the atoms together, the forces within the molecule, right? And so if we imagine, say, taking a water molecule and breaking one of the oxygen-hydrogen bonds, for example, to leave behind like an oxygen radical and a hydrogen atom like that. So we've taken the two electrons that made that bond and just pulled it apart. The force required for that is much, much higher, 493 kilojoules per mole. So it's an order of magnitude more energy. And so when we're talking about boiling water, what we're talking about is moving the individual molecules apart. We're not talking about ripping water molecules apart by adding enough energy to break bonds. We're not talking about the intramolecular forces or the internal bonds. We're talking about the bonds that exist, these relatively weak bonds that exist between the different molecules that make up the liquid. Okay, so that's one confusion. There's a second confusion that I want you to be aware of. And this confusion often occurs in biology, for example, where you have biomacromolecules, giant molecules, super long molecules that have many different groups hanging off of them. Say, for example, I'm just going to modify this water example here. What if we had a giant protein, and I'm not going to show the structure of it, but it had an oxygen with a hydrogen, we would call that an alcohol group, on one part of this giant molecule, and then it had all this structure, long structure, and it wraps back on itself, and then there's another oxygen hydrogen. Well, it's very likely, if those two things are held close in space, that there'll still be that positive charge, partial positive charge on the hydrogen, a partial negative charge on that oxygen, and if those two things wrap around, they're going to have this same attractive force, this 40 kilojoules per mole in the optimal arrangement and distance, and that's still going to be a force. Now, we would call that an intermolecular force, a force between molecules. But as it turns out, this is a force between the head and the tail of one giant molecule, right? We never call that an intramolecular force. We call it an intermolecular force because it's like two independent parts of the big molecule interacting, right? So there are multiple confusions about this terminology, intermolecular force. What we mean is the attractive force between groups, right? Usually, if we're talking about like a pure liquid or something like that, between two molecules or two atoms that make up that liquid. In some cases, when we're talking about giant molecules, we're still talking about intermolecular forces. Now we're talking about the head and the tail of a giant molecule coming together and interacting sort of the same way like two water molecules would interact, right? So there are confusing things that exist, and I'm just kind of clarifying. What we're going to call it is intermolecular forces, and what we mean are the forces between molecules in a liquid or molecules in a solid. We're rarely going to be referring to the intra variation. Okay, the other confusing part is chemists have adopted this term intermolecular force. The problem is that elements, let's think about helium, for example. We know helium is a gas, right? If we compress helium or we cool it down to 4 Kelvin, eventually it will become a liquid. The forces that hold individual helium atoms together are not intermolecular forces, they're interatomic forces because helium is an atom, but we still call them intermolecular forces. So this term intermolecular forces has become kind of generic for the attractive forces that hold particles, to be most general, together, say in the liquid or in the solid phase, right? They could be atoms, they could be molecules. We usually just say IMF, intermolecular force. The forces have the same origin, whether it's a molecule or an atom, and so we kind of just simplify by calling them all IMFs, even though sometimes we mean IAFs. Okay, so I've already hinted about it, but the reason why we care about this is intermolecular forces determine things like the melting point, the boiling point, the surface tension of a liquid, the viscosity of a substance depends somewhat on the intermolecular forces, the vapor pressure, how much pressure a liquid exerts into a vacuum, the binding properties, for example, if you wanted to talk about a small molecule binding some protein receptor or something, it's the intermolecular forces that govern that interaction. So it's really important to understand them and be able to identify them, and that's what this video ultimately is about. But I wanted to make sure it was clear what we're talking about first. So let's talk about a few things. Intermolecular forces. Now we're talking about types. There are kind of two giant categories, and it's pretty easy to tell them apart. We have the attraction between atoms of a metal within a metal. We call those metallic intermolecular forces, right? Or just metallic bonding. And as it turns out, metals arrange themselves very differently than molecular substances other molecular or ionic substances. So let's just look at kind of a crude picture of what a metal is like. So this is not to scale at all, but I just kind of want to give you a sense. Metals have nuclei with lots of positive charges jammed into the nuclei. And some of their electrons are held fast to that nucleus, some of the core electrons. But metals, we know, conduct electricity. And the reason why they conduct electricity is their outer electrons enter what's called a conduction band, meaning the outer electrons are actually shared with all their neighbors, right? So there's like each of these, say, metals has this core of electrons that is held tight, and this is again not to scale, that's held tight to the nucleus, the inner electrons. But then some of the higher energy electrons actually are shared between all the metals, and so it's kind of like nuclei in a sea of all of these little dots would have like a negative charge, right? There's like a sea of electrons around them, and that's the reason why electrons can flow through a metal, because these electrons could move. Say if you introduce an electric potential, they can move. They're not attached to the nuclei. They don't have to stay fixed in place. They can just move, right? And so that's what holds metals together. And now think about how hard it would be to heat a metal. You can heat a metal until it becomes in the vapor phase. What that means is one of these nuclei would have to like come out of the solid or liquid metal surface, right? You'd have to melt it first. We know we can melt metals, but it's still the same electron situation, this sea of electrons. And then you would have to provide enough energy to pull that nucleus out and suck up all those electrons, which are like in this conduction band. It's really stable for those electrons to move around. You'd have to relocalize them onto a nucleus and pop it out, right? That takes a tremendous amount of energy. And so that occurs at very high temperatures. And so I've just included one example here. Sodium metal, the shiny stuff that if you that has a zero oxidation state. You rarely see it this way, right? Because it's highly reactive. It wants to give up its outer electron. But if you take sodium metal and you try to boil it off and turn it into a gas, you have to heat it to 880 degrees Celsius. It's very hard to get individual sodium atoms to move into the gas phase, right? You can do it, right? You just have to heat it really, really hot. Okay, so that's one kind of intermolecular force. It's metallic. You know when you're looking at one of those because you see just a metal in its zero oxidation state, the shiny, malleable state of metals. When you're talking about things that are like salts or molecules, individual molecules, we're talking about a different kind of intermolecular force. Those are called the Coulombic intermolecular forces. So Coulomb's law is the one that tells us how that describes the force between two different charged objects. And so here's just kind of an abbreviated form of Coulomb's law. If you have a positive charge, that's what Q means, and a negative charge, they attract one another. We have that sense. So this is kind of the origin of that attraction between the things. And so if you have a positive and negative charge, they will attract one another with some force. The bigger the charges, either positive or negative, the more they will attract, or the closer the things are together. So R here is the distance between the two things that are attracting. So if the distance is small, the force is large. So if you put a positive and negative thing really close together, the force pulling them together is stronger than if they're further apart. And as it turns out, different intermolecular forces have different distance sensitivities. So some of the intermolecular forces only act when the things are like almost touching. And if you separate them at all, the force goes away. So they have to be really, really close in space in order for that to work. Other intermolecular forces, like, for example, ionic bonds, they can function at a much further distance. So the way we signify this distance sensitivity is by the power of R. If R is a high power, that means as R grows, that denominator is going to get large fast, and the force between those two things is going to diminish quickly. So the higher the power of N, the more sensitive the two things are to the distance apart. So for example, we have like a positive and a negative charge. This would be like an ionic bond. Those are, we're going to talk in detail about this in a minute, but those things are going to attract one another, and they're going to be less distance sensitive than some of the other intermolecular forces. Okay, and so I have here full charge representation. Usually we show a full charge, like an electron has a full negative charge, and the absence of an electron is a full positive charge. That's how we represent them. We represent partial charges. Oftentimes intermolecular forces exist between teensy-tiny charges that are very transient. We usually just show a partial charge as a small delta with a plus and a small delta with a minus. So those are partial charge representations. Okay? And just to give you a sense, intermolecular forces vary dramatically in their strength. So we just talked about, say, the boiling point of sodium metal is 880 degrees Celsius. That's really strong bonding between two different metal atoms in order to pluck one out of there. As it turns out, ionic solids, something like sodium chloride, also have very strong intermolecular forces. We call them ionic bonds, right? Just to give you a sense, sodium chloride has a boiling point of 1465 Celsius, so even hotter than sodium metal. It's very hard to, say, pluck a chloride out of a sodium chloride crystal or molten sodium chloride to put it in the gas phase. Okay? Very, very hard to do. Then we talk about things that are more familiar, like water, which has relatively strong intermolecular forces. It boils at 100 degrees C, so again, about an order of magnitude less. It takes about an order of magnitude less energy for a water molecule sitting on the surface of hot water to move into the steam phase, out into the vapor phase. Hydrogen sulfide, so ion-ion is another word for ionic bond. Hydrogen bonding is what is the strongest intermolecular force in water. Dipole-dipole force is the strongest intermolecular force in hydrogen sulfide. Its boiling point is -60, so obviously that's a much weaker force that's holding those together. And then something like methane gas, has even weaker intermolecular forces. You can make it into a liquid, so we know intermolecular forces are there, but they're much weaker with a -162 boiling point. So we're going to spend most of our time on the Coulombic intermolecular forces, and that's what we're going to do right now. Okay? So here in this little outline here, I have sort of all of the different ways we think about intermolecular forces. And I have the distance sensitivity of those intermolecular forces, so an abbreviated Coulomb's law next to each run. And we're just going to kind of go down this list. We're not going to do them in order for reasons that will become clear. So ion-ion, this is another word for ionic bonds. And we know that ionic bonds are the force that hold things like salts together. So we know that sodium chloride is a crystal, and it's going to form some kind of lattice, right? And there are going to be forces that are going to attract the sodiums with their adjacent chlorides, right? And there's going to be some repulsion forces actually between the chloride and the sodium and the sodium. But usually the intermolecular forces we think about are the attractive forces. These can be quite strong, right? These are full charges. So the force between two adjacent atoms in a crystal lattice can be quite strong. And also, because they're full charges, their distance sensitivity is relatively minimal. So it's like 1 over r to the 1. So you can actually move them quite far apart and they still will snap back together and try to remain attached, right? So it has a relatively low distance sensitivity. It also doesn't have an orientational sensitivity, right? You can take like a negative charge and put it anywhere around a positive charge and it's still going to attract. Other intermolecular forces don't behave that way. So ion-ion forces are strong, sort of the strongest type of intermolecular force on the Coulombic side. Okay. Another type of intermolecular force is the ion-dipole force. And so you learned about molecular shape and how you can understand whether a molecule or a bond has a dipole last semester in high school. And so we know, and I've already talked about it in this video, like oxygen has a partial negative charge, this hydrogen has a partial negative charge or partial positive charge, this hydrogen has a partial positive charge. So when you take salt, table salt, and you put it into water, it dissolves. And the reason why it dissolves is that the positive charge on the sodium ions forms a strong intermolecular force with the negative charge on those oxygen atoms. And similarly, the hydrogen atom with the partial positive charge forms a strong intermolecular force with the chloride, right? And so these things out here are ions. Things that have charges are ions. And so these are full charges out here, right? This is like a full plus, and this is a full minus, having an interaction with a partial plus or a partial minus. So we have ions here, chloride or sodium, and we have a dipole, right? Partial charges on that dipole forming an attractive force. So this is also a relatively strong force. It's not quite as strong as an ion-ion force because the charges are smaller, and it also has more of a distance sensitivity, right? So as you increase the distance, that force is going to drop away more quickly, okay? just to give you a sense, sodium chloride, a salt dissolves, 36 grams of salt dissolve per 100 grams of water at room temperature. So that's quite a lot of a substance dissolving. And the reason why so much dissolves is it has this really strong intermolecular force between the ions that are in the crystal lattice and the water, the bulk water. Okay, so let's now talk about hydrogen bonding. So hydrogen bonding is a very specific case of dipole-dipole forces, and it only occurs in very specific situations. Let's start with the one that I think you're familiar with, which is hydrogen bonding in water. Hydrogen bonding in water, I've already sort of talked about it. Hydrogens in water have a partial positive charge. The oxygen has a partial negative charge. And there's a intermolecular force between the partial positive and the partial negative charge on the oxygen and hydrogen, respectively, on two adjacent water molecules, right? That's a partial charge with a partial charge, so that's like a dipole interacting with another dipole. So the positive of one dipole interacting with the negative of another dipole, right? And, it's not limited. It's sort of happening sort of all over the place, these kinds of interactions. And in fact, we could imagine water, liquid water, being kind of this dynamic situation where one water molecule might be having hydrogen bonds with 2 or 3 different neighbors all at the same time. It could have a maximum of 4, right? Because it could have one hydrogen bond here, one hydrogen bond there, one hydrogen bond there, and one hydrogen bond there. So like in ice, that's what happens. Every water molecule is involved in 4 hydrogen bonds. That's like the optimal arrangement. In water, they're kind of moving around. So you don't usually have 4 happening all at once, but maybe like 2.5 or 3 are happening, right? And so water has this very high boiling point of 100 degrees Celsius. That reflects this unique thing that we call hydrogen bonding. It's a unique dipole-dipole force. And it's really important that you understand when those things can occur. So hydrogen bonding only happens in certain situations between very particular, between very particular atoms. So in a hydrogen bond, what you have is you have an interaction between a hydrogen and some other atom, right? And so I'm going to be super careful here. This is the hydrogen bond I'm talking about. This atom X can be an oxygen, it can be a nitrogen, or it can be a fluorine, okay? This hydrogen right here is the one, we call that the hydrogen bond donor. It's the one forming the hydrogen bond. So this element right here is going to have a partial negative charge. This hydrogen right here has the partial positive charge. And only hydrogens that are bound to an X, which means that one also has to be an oxygen, a nitrogen, or a fluorine. So you only expect to see hydrogen bonds when you have hydrogens bound to oxygen, nitrogen, or fluorine interacting with an oxygen, nitrogen, or fluorine. Those kinds of bonds, those kind of intermolecular forces are unusually strong. They're unusually strong. It's a perfect sort of balance of partial charges and distances. It makes for very strong intermolecular forces. Unusually strong. They are dipole-dipole forces, but they're a unique class of them. They behave differently. Just to give you an example, hydrogen sulfide has the same kind of polar structure as water, and it forms sort of similar, I'm going to switch back to purple here, it forms similar intermolecular bonds. Those bonds are much, much, much weaker. The boiling point of water, as we know, at atmospheric pressure is about 100 degrees C. The boiling point of hydrogen sulfide is minus 60, right? That bond between those adjacent molecules is so much weaker, or those bonds between adjacent molecules is so much weaker, it's really easy to bring an H2S molecule, a hydrogen sulfide molecule, into the gas phase because it's so weakly held by its neighbors. It occurs at a much, much lower temperature, right? 160 degrees lower. That's an enormous difference in temperature. And it reflects this difference in the strength of the intermolecular forces in liquid hydrogen sulfide versus liquid water. So one skill you need to practice is making sure that you can identify when hydrogen bonds are possible. And those are likely going to be the strongest intermolecular force that exists in a substance that can have them. Okay? So that's super important. The distance sensitivity of all dipole-dipole forces is 1 over r cubed, which means they do sort of diminish relatively rapidly as you pull the things apart, because every time you pull it apart a little bit, it's r cubed, right? So as that number gets bigger, the force between those things drops off quickly. Okay, so that's super important. Another interesting thing about hydrogen bonding is that it's orientation sensitive, right? Like in order for this to work, you have to have this positive and that negative pointed toward each other, this positive and that negative pointed towards each other. So the way a lot of people illustrate it is you've got to have the poles kind of lined up. Like if you have a molecule like this, and it's going to interact with its neighbor, it's got to line up with the dipole such that the positive and negative can get together. In fact, it's a big advantage. It makes for a stronger hydrogen bond if the things are aligned like this, right? Those poles are aligned like that. It's better, say, for example, than this alignment, which is less good. Like if it has a positive here and a negative here, like that hydrogen bond would still work, but it's going to be a weaker hydrogen bond. So a well-aligned hydrogen bond is one where the poles are sort of lined up with one another. So hydrogen bonding, unlike ion-ion bonds, for example, has orientational sensitivity, meaning you got to get it lined up and you have to have it pretty close, and then you get a nice strong interaction. Okay, so there we go. So now let's talk about dipole-dipole forces. So I've already sort of described what they are, and you have molecules that have permanent dipoles, like HCl, for example, has a permanent dipole, right? There's a positive here and a partial positive here and a partial negative here, interacting with a partial positive here and a partial negative here. This has all the characteristics. So HCl gas, right? Hydrochloric acid is actually a gas. We deal with it in a liquid, but it's just dissolved in water. Okay, there's an intermolecular force that holds those together. It's a fairly weak intermolecular force. The boiling point's minus 85 degrees Celsius. We know that it's related a little bit to HF, which is another hydrohalic acid, but HF has the potential to hydrogen bond because this is a hydrogen bound to fluorine, bonding with the negative pole of a fluorine, right? And so what you can see, here's the sort of dramatic difference. This one up here is a hydrogen bond, 67 degrees Celsius is the boiling point. HCl is minus 85 degrees Celsius. It's still a dipole-dipole force, but it's much, much weaker, right? So this up here is not a dipole-dipole. That is not a dipole-dipole. It is a H bond. It's a subcategory of dipole-dipole. And then this down here, that's a true dipole-dipole. It's where it's not hydrogen bonding. Just to give you a sense, HF has a molecular weight of about 20. And HCl has a molecular weight of about 36. Usually things that have higher molecular weights, if they didn't differ in other ways, would have similar boiling points. And you can see they don't because the hydrogen bonding is so dramatically different. Another molecule that has a similar molecular weight is molecular oxygen. But you know that molecular oxygen doesn't have a dipole. It actually lacks the ability to have dipole-dipole forces. And you see that its boiling point is minus 182, even though it has a similar molecular weight at 32. So you can see the forces between adjacent oxygen molecules in the liquid phase of oxygen is much, much weaker. It's much easier for an oxygen to sort of leave that. It takes at a much lower temperature, oxygen molecules can leave the surface of liquid oxygen. Even though they have similar molecular weights, the boiling points are radically different between these three for different reasons. The top one because of H bonding. The middle one has dipole-dipole forces, which are moderate force. Oxygen can't dipole-dipole. It does dispersion, which we're about to talk about, but it has a much lower boiling point because the intermolecular force is weaker, even though all of them have sort of similar molecular weights. Okay, so let's move on and talk about dispersion. I'm going to talk about dispersion sort of in the opposite order. I'm going to start by talking about what we usually refer to as London dispersion. London dispersion occurs between atoms or molecules that have no permanent dipole. Okay, and so what I've drawn at the top here is an illustration of a helium atom, right? So this is a helium atom right here. It has a nucleus with 2 protons in it. At any given time, it has 2 electrons sort of whizzing around. Helium is an atomic gas, meaning it doesn't like to form molecules, right? It's one of the noble gases. And imagine at some point in time that both the electrons just are whizzing around that nucleus, and they just happen to be on that side of that nucleus. At that moment, if we sort of like drew a circle around it, and we had to say where are the charges associated with that? We would say there's like a partial negative charge over here because all the electron density is kind of on the left, and there's a partial positive charge over there. So that's kind of an instantaneous dipole. It's not kind of an instantaneous dipole, it is an instantaneous dipole. That means if something were nearby it, it would say, hey, that thing next to me is a dipole. And as it turns out, like when you're talking about helium in the liquid phase, there is something next door. That's the helium atom that's next door. And so it's going to say, gosh, there's a positive charge here, and its electrons are going to be drawn to that side. They're going to be pulled in that direction, and it's going to create a little minus dipole there and create a little positive dipole there. And the same thing's going to happen to its neighbor and its neighbor and its neighbor. Now those movements of electrons are happening super fast, so they're very transient. So we call these like instantaneous dipoles. They happen just in an instant, but they kind of ripple through the whole liquid. And while they're in existence, I'm going to just pick another color. While they're in existence, there's an intermolecular force that exists between those two. We call those very transient intermolecular forces dispersion forces. If it's between two things that are uncharged, we call them London dispersion forces. London dispersion forces are super sensitive to distance because these are tiny, tiny dipoles. So you have to get two atoms or molecules very close together to have that attractive force occur. So here's an example with helium. Helium has a boiling point of minus 269 degrees Celsius. That's almost 0 Kelvin, right? That's 4 Kelvin, almost absolute zero. And so this is an extremely weak force. Before those helium atoms break apart into their lone atoms floating around in space. So dispersion forces depend on a couple of things. One, it depends on how easily the electron cloud can sort of distort, and we call that polarizability, how polarizable the electron cloud is. Things that have a lot more electrons, atoms that have a lot more electrons, the outer electrons are more shielded from the nucleus and they more easily distort. There are softer electron clouds. So in helium, the electrons are held really close to the nucleus in those 1s orbitals, right? And it has a boiling point of almost absolute zero. If you go up to argon, which is also a noble gas, so it's an atomic gas, its outer electrons are held in 3p orbitals. So those orbitals are much further from the nucleus. Those electrons are much more distortable. And what you see is the boiling point goes up to minus 186. It's still a very low boiling point, but that means the intermolecular forces between adjacent argon atoms is much stronger than that in helium, where you have to get down to almost absolute zero. If you go up to iodine, and here I should show these are like I2. This is molecular iodine coming together. Molecular iodine has no permanent dipole, right? It's two identical iodines held together. They've sort of formed like watermelon-shaped molecules, right? It's like I like this, and there's this electron cloud around them. Those outer electrons are held in 5p orbitals. So, several quantum shells, principal quantum number shells, have been added, and so they're enormous compared to argon and even more enormous compared to helium. And the boiling point of iodine is 184. Okay, so again, another enormous change in boiling point. And the reason why is polarizability. Those electrons can be easily distorted. So this force between two distorted electron clouds is much higher because the electrons more easily distort. So polarizability is one key thing that determines the strength of intermolecular forces when we're talking about dispersion. Okay, dispersion. The other thing that determines the strength of dispersion forces is the surface area, right? So if you have two helium atoms, it's a tiny, tiny surface area coming together. It's like the just sort of a tangential interaction between two different spheres. You're just getting a small contact area, and that's the only place that intermolecular force can exist. That's similar to like two methanes, right? So methane is a tetrahedral molecule, but the electron cloud around it kind of looks like two spheres. And the electrons in those hydrogens are also held in 1s orbitals. It's fairly hard. It's not very polarizable. And so there's this small intermolecular force that exists in liquid methane. It boils at minus 161, so Substantially stronger intermolecular forces than alone helium, but two molecules now coming together have sort of a weak intermolecular force. You know, the polarizability of a molecule like propane is very similar to that of methane. So the electrons are all held in the same kinds of orbitals, but the beauty of propane is you can get two propane molecules and you get a very large surface area, and across this whole surface area, you can get instantaneous dipoles. And so there's a much bigger chance you're going to get lots of sort of larger surface dipole or instantaneous dipole dispersion forces between two larger molecules. And for that reason, it's not just that there are more electrons there, it's also that you have this surface area interaction. London forces go up. So the boiling point of propane is minus 43 degrees Celsius. It's a gas room temperature, but it condenses at a much warmer temperature, right? More than 100 degrees warmer than methane condenses because it has stronger intermolecular force. It's got a bigger area. So dispersion forces are determined by two things. One, the polarizability of the atoms involved. So if the electrons are loosely held on those atoms, it's more polarizable, stronger dispersion forces. Or if there's a big surface area where the molecules can interact, the bigger the surface area, even if polarizability is similar, the bigger the surface area, the stronger the force between. Just more opportunities for dispersion to occur. Okay, so enough on dispersion forces. Dispersion forces are the weakest of them all, and they have very high distance sensitivity, meaning you separate them a little bit and the force goes away. So you can also have things like dispersion forces, which are induced dipole forces. So, for example, molecular bromine doesn't have a dipole on its own, but if you put it next to water, where this hydrogen atom has a partial positive charge permanently because it's a dipole, what that's going to do is it's going to distort the electron cloud, and I'm just going to kind of show it like this. It's going to distort the electron cloud around these bromine atoms, and it's going to put more of the negative charge here and more of the positive charge over here. So that gives a stronger intermolecular force here. So this is like an IMF. That would be stronger than just a dispersion force where it's two nonpolar molecules coming together, because you've got a permanent dipole, and you've got an induced dipole. So this is going to be a weaker pole, this is going to be a stronger pole, so it's stronger. The distance sensitivity is also kind of in between, somewhere between 1 over r to the 6th and 1 over r to the 3rd. So it's a little hard to quantify it, and we're never really going to be doing math with this. You can see that this force also depends on polarizability. So bromine dissolves, 42 grams of molecular bromine dissolve in 1 liter of water. Okay, and that's because this intermolecular force is relatively strong. Chlorine, which has its electrons in smaller orbitals, they're more tightly held, it's less polarizable, you can only get 6 grams because there's less electron density to kind of, like the electrons are held more tightly. So you're going to get some distortion, but it's going to be a smaller pole, and so that makes this force weaker. And so the stronger the bonds to something that's dissolved in water, the more of it will dissolve. That's why we saw so much salt dissolve in water. A lot of bromine will dissolve in water because of that strong intermolecular force, because bromine's so polarizable. Much less chlorine, right? And if you looked at fluorine, it'd be even less, because they're not very polarizable. Similarly, you can't get very much oxygen, say, for example, in water. You can't get very much helium gas to dissolve in water because the intermolecular forces are so weak. It's easy for those gas molecules to just pop right back out. Okay. And finally, the last force that I'm going to talk about is ion-induced dipole. So I'll just use this example. Like, you could dissolve bromine in a solution of hydroxide, and whenever bromine encountered a hydroxide, of course there's going to be this huge distortion. Oops, and I drew it the wrong way. There's going to be this huge distortion where the negative charge on the oxygen pushes all the loosely held electrons over here, so there's going to be a negative pole set up. And this bromine nucleus on this side is going to be exposed, and that's going to set up a strong intermolecular force, right? So this would be an example of an ion-induced dipole force. These forces, as I have them listed here, are kind of in strength order. Ion-ion, ionic bonds are the strongest, ion-dipole next, hydrogen bonding next, dipole-dipole next. The dispersion forces are the weakest, but ion-induced dipole would be next, dipole-induced dipole would be next, and London would be the least strong. All right. So now, classification. So when you're given a substance, it's important that you be able to identify the intermolecular forces. The first main classification is this thing a metal in its zero oxidation state, like sodium metal or iron metal? If so, we're talking about metallic intermolecular forces, and we know they're very, very strong. If not, what we're talking about is coulombic forces, right? So coulombic forces are the ones we've just been chatting about. If you want to understand which coulombic forces are at play, you've got to know the three-dimensional structure, because you have to know whether the molecule or the bonds within the molecule have dipoles, right? That's how we sort of distinguish them. So the first thing you have to do is determine the three-dimensional structure and identify any dipoles. So if you're given a molecular formula, you need to use your Vesper technique to draw a good three-dimensional structure. So draw a Lewis structure, draw a Vesper structure, then identify any molecular dipoles and even any poles and bonds. And then you also need to consider the polarizability of the atoms involved or the surface area. If it's a giant molecule that's not polarizable, it might have strong dispersion forces. Or if it's a small molecule but it's got bromine atoms or iodine atoms or something highly polarizable, those are going to have stronger dispersion forces. So these are all things that help us classify. And then what you're going to do is you're going to predict all the intermolecular forces that are at play and then try to figure out which the strongest one is. So when you can start out, you can rest assured that all molecules have dispersion forces. Regardless of the presence of poles or anything else, everything has the dispersion force. So you can say, check, it has a dispersion force. But that's going to be relatively weak compared to some of the other ones. And then what you have to do is determine what other intermolecular forces are present. Is there a dipole? Is there an ion? Could there be an ion dipole? Are there two full charges? Could we have an ionic interaction, right? So you need to work through that. And then you sort of use that listing that I had on the previous page of the relative strengths, and you decide what the strongest force is. That's likely the one that's going to sort of determine the properties of the substance. Sometimes it's hard to tell, but that's the way we do it. So let's just do one quick example. In a pure sample of NF3, nitrogen trifluoride, determine all the intermolecular forces that exist, predict the strongest intermolecular force and explain why it is the strongest, and then draw a picture of two molecules of the substance, not of each substance, just of the substance interacting via the strongest intermolecular force. So when we think about nitrogen, we might consult the periodic table, but in its valence, it has 5 electrons, and each fluorine has 7 valence electrons. So if we want to assemble a Lewis structure, what we're going for right now is we're trying to figure out the three-dimensional structure of NF3. And so the first thing we'll draw is just a Lewis structure. So when I draw the Lewis structure of NF3, I can get everything to have an octet if I make a single bond between each fluorine and the nitrogen, and then I have a lone pair on the nitrogen. Now I use my valence shell electron pair repulsion model, and I know that the best way to arrange 4 kind of electron valences like I have here, I have a lone pair and 3 bonds, is in a tetrahedral-like shape. And so I would say, one valence is going to hold the lone pair, and then each of the other valences is going to hold a fluorine, right? And I'll go ahead and drop in the electrons just to make sure it's clear. So I'm just using valence shell electron pair repulsion model here. And so I know that I have a trigonal, a trigonal pyramidal molecule here. So that's good to know. It's not planar, it's trigonal pyramidal. And now I have to assess the dipole moments. Well, fluorine I know is the most electronegative element. I don't even have to look it up. So I know I have got dipoles going this way, right? And so I kind of have 3 sort of bond dipoles where the dipoles all put a partial negative charge on those fluorines, right? And I have a molecular dipole that's going to sort of be the sum total of those 3 dipoles. So if I was thinking about the molecular dipole, it would be like that. And that means this nitrogen has a positive dipole. Okay, so now we're thinking about predict the strongest intermolecular force determine all the intermolecular forces. Well, I've got a molecule that's polar. So I know I've got dispersion and I've got dipole forces at least. Is it possible to do hydrogen bonds here? Nope, there's no hydrogens. So that's not possible. I certainly don't have a hydrogen bound to a nitrogen, oxygen, or a fluorine because I have no hydrogens at all. So dipole forces seem like they're the strongest. Now if I wanted to illustrate, so the 2 forces I would predict here are dispersion and dipole. being present here. And then if I wanted to know which is the strongest, well, between dispersion and dipole is the strongest. So I would estimate that that's probably the key intermolecular force in this molecule. And now let's draw a picture of two of these molecules interacting. And so here I'm going to sort of dispense with all of the extra stuff. Oop, I didn't mean to draw a hydrogen there. I'm going to sort of draw a fluorine here, and a fluorine here. And I know there's a partial negative charge there. And so I'm going to try to line up like one of these nitrogens, right? It seems weird having a nitrogen being the positive, but I'm going to do it. So nitrogen has a positive, and so if I wanted to illustrate that intermolecular force, there it is. It's between those two poles, and this is a dipole. Dipole force, that's the strongest intermolecular force. So if I wanted to draw a picture of it, that's what it would look like. And of course I could continue and I could draw another nitrogen over here having an intermolecular force, and I'll go ahead and draw it like this, and we could show a second molecule in this liquid nitrogen trifluoride. Nitrogen trifluoride, as it turns out, is a wicked greenhouse gas, but there's more and more of it being produced all the time because it's used to make a flat screen displays. So I'm like looking at a flat screen display here as I'm making this video, and so this stuff is a real problem. It's a gas at room temperature, a gas at normal temperatures, and goes up into the upper atmosphere, and it's not a great player in the upper atmosphere for reasons of being a greenhouse gas. So in any case, I hope you found this video useful about intermolecular forces and classifying and characterizing them.